Okay, so today will be the last lecture before the Thanksgiving break, and so we don't have class on Wednesday, Friday. I will see you next week. So um, after today, we should have covered all the basics about DuckDB, the SQL basics, how to do data import, export, how to do some spatial relationships and visualize. And today is going to cover spatial joins. So it's really more like common JS operations. How do you do intersection? How do you figure out the buffer? How do you figure out selecting something within a certain distance or selecting something being contained with something? So those are some of the common ones that can be useful if you need to do some spatial analysis. And keep in mind, again, the DuckDB spatial extension is still preliminary. There are not a whole lot of like advanced one. But this basic one at least can give you some equivalent functionality that if you use desktop JS. And it gets a little bit more complicated now because you need to write many lines of SQL statements. But you can follow examples. And like I said, if you need to do something, you can just Google or ask ChatGPT. I'm not sure ChatGPT will still be there for how long. You probably heard the saga about over the weekend. So now some of the like previous CEO are hired by Microsoft now, so it's no longer. Anyway, it's a funny story to follow over the weekend. So use it when it's still available. So and most of the SQL like statements you use in other spatial database are also applicable to DuckDB. As long as you have the same function, you can use it the same. So even though you might not find a lot of documentation online, but you can just find those statements they use for PostGIS or other spatial database. Kind of very much similar. And I also posted a lab 10, so that will be the last lab that the last lab we have for the semester. And since we don't have class for the on Wednesday, so I extended I think the until the end of November. So you have until I think next Thursday to work on the lab assignment. Okay, if you need more time, let me know. And then you should work on your final project. We might have a quiz, the last quiz next week. Okay, sometime, and then we'll be done for the semester. So you have not started your final project. Now is a good time to do that. Questions? So for today, we're gonna just quickly go through some of these. Let me see which one I'm gonna use. Yeah, this one. That's fine. And so for lab 10, I think I asked you to. So this one here for the lectures, I already created a DuckDB database for you. But for that time, I actually give you the original vector data. Ask you to import to create the DuckDB database you're going to use for the assignment. So here, I'm going to download this one, and then now you should be familiar with this. I'm going to use the spatial extension, and then in there, I'm going to show you, for example, the data tables. Yeah, the data tables within the database. Right, so you have 1, 2, 3, 4, 5, 6, 6 tables in there. And for this lecture, we're just going to utilize 2 tables. The first one is the subway station, and the second one is the NYC neighborhood. So the first, before you do like spatial analysis, usually you want to see what a table look like, and maybe potentially visualize the data if you want to. So keep in mind all these data tables. The projection is EPSG 26918. Okay, so that's the UTM zone 18. Like I mentioned before, DuckDB right now doesn't have the capabilities to store the projection information inside the database. It might be added in the future, but for now, you need to know when you import the data into the database what projection it is. You need to keep it somewhere. Otherwise, the database has no idea, because when you display the point, the leg long, or the XY, it have no idea about what it is. It just knows it's a number. So, and that's why I put in there in case later if you want to, for example, calculate the distance, then you need to actually know whether it's unit feet or meter, or is it degree? Okay. So for now, because it's UTM zone, so it's using the meters. So the unit is meters. Just to keep it in mind. So first, let's show, for example, the first 5. Then you see here, this one is the NYC neighborhood, right? So you see the number. These are not leg long, okay? These are the UTM zone, so it's meters, and that's why you can calculate the distance from one point to the other. When you import the data into a database, if it is leg long, then you cannot calculate the distance. You need to actually convert the projection to something that you can calculate the distance. Degree, you cannot, because there's no projection. It's just a graphical, geographic coordinate system. So right now this is good because later we're going to calculate distance. But I just want to let you know, these are the x, y. So basically it's meters. I'll show you the first 5. And similarly, this one is the subway stations. Similarly, show you 5. And so for the neighborhood, we only have 3 columns. It shows all of them. For the subway stations, it has a lot more columns. So you will see the dot in here. This one actually is a bit annoying. Sometimes you might want to see all the rows, and here you cannot see. So the alternative would be, how do you see all the columns? How do you see all the columns? You can maybe convert to a data frame. And here you should see all the columns in here. Sometimes even if this is too long, it might also not show you. Then you just dot columns. Eventually you can get all the columns. But once you transform to data frame, this one is no longer in something you can read. So you can just do column. Oops. Alright, so here you eventually will be able to see all the columns if you want to. Next, let's do some spatial analysis. Okay, so let me maybe open the website just to show you some of the. I think we mentioned last time, but I want to basically show you some of those. DuckDB, and if you go to the documentation, then under the extension spatial here, so scroll down. Right, so these are the construction and then conversion, spatial properties, and the spatial relationships here. So what we're going to use is some of these functions. So you can think about within that means you're trying to figure out the 2 geometry. So here we have one column, this the other column. Kind of like this is like ArcGIS select by location, like something within something touches something, overlay, contain, crosses, intersect. So here, let's go back to this one. What we're trying to do is that, okay, I want to select the neighborhood that where this Broad Street subway station is in, right? So it's simple, basically a point to a polygon. You find out, you know this point, and you want to find out what polygon this point is in. And so this is a common type of spatial relationship. And you will notice right now, this gets a little longer and longer. So it's no longer one line of equal statements. And so just to give you kind of a big picture what this one is doing. So basically you need to intersect 2 vector data set, and you need to basically join them so that you can analyze them. And forget about the select first. You look at these 2 lines first. These 3 lines, okay? From the neighborhood, A is something, basically we rename the neighborhood as NYC neighborhood as neighborhoods. Sometimes just make the name a little bit shorter, and then without the underscore. And this neighborhood join the NYC subway stations. Again, give it a new name, a subway. And what this one is doing here, on ST intersect. So what this one is doing here, I'm going to instead intersect the neighborhood vector data with the subway vector data. And then which one I'm going to intersect, I'm only could find out to the one where the subway name equal to Broad Street. Okay, so the subway, if you go back to this one here, right? So the subway has, oops. So there's where's the name? In here, okay? So the subway has a name column, and that column there's one called Broad Street. And also what we're trying to do is, okay, I have the neighborhood vector data. I have the subway neighborhood data. I want to select the subway where is the Broad Street. and then intersecting that one with the neighborhood. So basically you're selecting the neighborhood, and then you can figure out, you can decide which column you want to return. Otherwise, you can just select star. It's going to return all the columns from the neighborhood table. In this case, I want to also going to select the name of the subway station, the name of the neighborhood, and also the name of the boroughs it is in. So basically, this one here, right? Subway.name, neighborhood.name, and then it's because we earlier we renamed it. Otherwise, it'll be NYC underscore neighborhood.name or something. So usually, if you have multiple tables joined together, you want to rename it a short name, and then so they can utilize data. So take a look. All right. So this shows you basically which neighborhood it is in, and also you can edit as many columns that you like from the resounding table. So of course, this is just a data table. We don't return the geometry. So if you want the geometry, you will need to basically select something from there. You need to include the geometry. So later on, if you want to visualize that, you can visualize that. But for now, we are just selecting this, which one is in, right? So the name equal to this one. So you're welcome to change it to other, right? So if you see here, we have a kinds of names in here. I can maybe change to how about this one, Rector Street, right? And so I can change to here. Oops, it should select a different one. Okay, build one again. This one actually has multiple. There are two Rector Street subway stations in there, so you select two. Make sense? So this is essentially if you in ArcGIS, QGIS, you open two step files in ArcGIS, and then you say select by location, and then you say intersect, and then the source and the target, the source and the destination, it will select some of those, and then you can do whatever you want. But this is more like automatic way, because you might have a lot of subways. And the naming here, this one, you can select multiple if you need to. But right now we're only doing just one. Okay, make sense? Again, just read it usually from the from first, and then join, and then go back to like after you select, figure out what result you want to return. Otherwise, you select from the beginning, sometimes it's a bit annoying because you don't know like subway. So actually, the subway come from here, the neighborhood come from here because you renamed it. And then so next, let's look at more. Like we have a lot of subway stations, and different subway stations, they have a different color, right? So basically, this is where you but if you go online, if you search like let's see if I can show you NYC subway map, and if you look at the map, actually here, right? So they are locked. No, not this one. Actually, just this one, right? So subway lines have different color, and you can do some analysis. For example, I can select the subway line blue, and then I can figure out, for example, what neighborhoods intersecting with this blue line, because they are going to be a lot of neighborhoods. Make sense? Or I can select streets. How many streets intersecting, crossing this blue line? Or I can select what are the streets within 200-meter distance to the blue line, or whatever line you want to analyze. Make sense? So there's left hand actually have some questions asking how do you figure out the blue line? How do you select the blue line? All the subway station. How do you select all the streets within 200-meter distance to that? So these are some of the very common spatial analysis you can do directly within the database. So here we already show you all the colors, right? From blue, green, oranges, whatever color. There are actually 29 different colors from the for the subway. So next, let's figure out like what simple one. What neighborhoods the red subway stations are in, right? So if you come back to here, there should be some of the blue red one in here. Right? You might have multiple, but this is right now. We select all the stations that is the red color, and we figure out what neighborhood they're in. So again, right, these are pretty much similar. From the neighborhood, we will rename it as neighborhood, the subway, and then intersecting. So keep in mind here, intersecting, you are intersecting the geometry, okay? Because this column, this step file, is the geometry column, right? So if you come back to here, GOM, and so compared to the previous lecture, if you remember that we are intersecting a point, ST from text. Right now we are intersecting two geometry column, and then we're going to return, for example, the similar, the name, the neighborhood, blah blah blah. But right now we have a where clause here saying that if the subway color equal to red, then we select all the neighborhood, return the result, right? So if you run it, see, so this shows you 49 rows. So that means there are 49 neighborhoods. So that means this red subway passing through 49 neighborhoods. The same like if you're doing spatial select by location using ArcGIS or QGIS. Right? But the good thing is that you can customize whatever information you like. It doesn't have to be these three columns. So usually in the desktop GIS, you will just select all the things that from the original table. So if you select all the columns from the neighborhood, but right now you can actually customize point, line, polling, whatever information. So here, right, subway name, you can also add more information. So if you want, like here, the subway, right, we have a lot more information here: color, express, close, or even the geometry. Okay, so for example, if you just want, or you want the geometry coming from here, but you can add more information about the subway, because subway has a lot more information here, so you can add it directly to the resulting data table. So for example, I say express, for example, right? So I can come back to here and I can add, what is it? Okay, and it says subways dot express as express. Okay, on it. Oops. Where? Oh, comma, yeah. So comma, on it. See, so right now you can see add another column. So this is way more flexible. Basically, you can do the spatial join, and then you just figure out what you want to return. You can get any information from those two tables to input, rather than desktop GIS only can get information from one table from the neighborhood, right? And here, after that, you can do aggregation. You can see, for example, I can ask another question. Okay, so select all the neighborhoods passing through, for example, intersecting with the red line, and also it's express, right? Because right now you return this as a new column. You can save this one as a new table, and then you just select rows where the express column equal to express. Then you select. Basically, you can filter more, continue to filter more information from that if you want to. Questions? So that's just the simple basic intersection. Next, let's talk about the distance within. So this one is going to give you more information, like if you need to do some buffering, right? You want to find out, for example, if we give you some data set, let's say you go to UT here, you want to find an apartment, and assume that you have an apartment data set, and you have the school, the location, and you want to find out, okay, I will only want like 10 minutes walking distance. I want to find an apartment within 10 minutes walking distance. Then this is the exact user case you want to do here. Is give you two data set, and you want to find anything within a certain distance. Then there's a function called st within distance. I'll show you later. But for now, let's look at this two data set. So we have the NYC census block. Okay. So if you need to look at the data set first, that's why show this one just to look at what's in there. So from NYC census block limit 5. What? Oh, not census. NYC census. Okay, just show you the first one. So the census block, we have columns, population, white, black, Asian, and others. So here, again, it doesn't show you all the columns. Maybe convert to a data frame. You see a little bit more. Right, total population, white population, black population, Asian population, and others. And so what we're trying to do here is, okay, we can calculate the percentage, right? So this is all the populations, and we already have the population total column. What you can do is like this one divided by this one, so we can create new columns just to show you the percentage rather than the absolute number. So this one, you say 100 multiplied by sum, all the population, and then divided by the total population, and then it's what percentage from the NYC neighborhood. That means for the result in here. From NYC. Oh, this is all the aggregation. If you don't use the sum, just that column, you're gonna add a new column. So this one basically will show you aggregate the total population and aggregate all the white population, aggregate all the black population, and then divide it by the total population. So in total, there's 8 million people living within NYC. So this is all the NYC neighborhood, and you can see in total there are 44% white population, 25% black population. So if you want, I can, for example, I can also calculate the in here, comma. Oops. Here, Control C, Control V. I can do, for example, also the Asian population. Okay. In. Multiple comma here. All right, so Asian is 12%. So this you basically do the aggregation simply just by summing all the rows and then just do the number. And so let's take a look at, for example, different routes in subway. So what we're trying to do here is like to figure out the ratio, basically access to the subway, different populations, so who are living close by to a certain route of the subway. Basically, there's not going to be even because some subway may be passing through rich neighborhood, some might be passing through poor neighborhood. So you can figure out, for example, what are the people living within the, for example, 200 meters within the subway. So these are show you all the routes, like A, B, C, D, E, F, and there are lots of in here, 73 in total, unique routes of all the NYC subway stations. And then you can say, okay, you want to find out all the subways that starts with A. So this one here shows you like select listing all the routes from the NYC subway stations. This line used to be quite familiar now. And then we have a where clause in here. Where means, okay, any subway stations. So strPOS, basically the string position, and then so it's going to return the first occurrence of the string appear in there. So you will see here we have AC, ABCD, something like that. So basically I'm going to find A within that string. If it's in there, it's going to return the index of A appear. So it's kind of like the position. So if it is greater than 0, that means it exists. Okay. If it is not greater than 0, that means A doesn't exist in that string. So what we're trying to do here is, okay, find me all the routes. From this table, anything contains A in there. Okay. And you can see how many lines in there, right? So A, B, C, D, blah, blah, blah. So in total, we have 4, 6, 8, 9. So I have 9 routes that contains A in there. Make sense? So this one, just make sure they understand that where close. I think there should be another function, okay, like str contain. I'm not quite sure, but if you simply want to find something like start with A, you'll be str, like kind of like Python starts with something like that. But this one basically is contain. If it contains a string, we select all the routes. And then let's look at this one. Okay, it gets a little bit more complicated now. But again, forget about the select first. Just look at the from, the join, and the on. Look at this four, and then you go back to see the result, what you want to return. So what we're doing here, we're gonna, from the NYC census block, rename it as census, and then go to join the NYC subway stations, a subway. And this is the function where you can do the spatial join on STD within. So the distance within something, and then you're gonna pass in two vector data set. Also passing the distance. So this is 200 meter because it's already UTM 18. So we know it's actually the unit is 200 meter. So what we're trying to do here is, okay, select all the census block that are 200 meters within the subway. 200 meters here within the subway. And this is what subway you are focusing on. So where the subways contain the A in its route. Make sense? And then you go back to the plus one. So you select what you want. So again, we're doing the population calculation here. So for all the subway lines, it's going to sum up the entire population, white population, divided by the total, and then get the percentage. And similarly, you can get the black population and also the sum, something like that. So this is basically doing the spatial join of two data sets, but you're only focusing on a subset. So you have all the subways, you want to select all those subways that contain the A route, and then you find out the neighborhood, and then you decide what information you're going to extract outside this one. Okay, and you see that this is going to take a little bit longer because you are actually doing the spatial join on the entire data set and doing aggregation. So now you can see within this A route subway stations, there are overall 189,000 people living 200 meters within this subway station, and in total there are 45% white population, 22% black population. Make sense? So just read through line by line, and then eventually you can do it. But if your data set is pretty big, like millions, this might be a little bit slow because right now DuckDB doesn't have the spatial indexing. So spatial indexing is very important if you're doing the spatial analysis. If you just simply select row something like equal to something, it doesn't need to spatial indexing. But if you're doing the spatial geometry join, something like that, this one needs spatial indexing. So it'll be pretty slow if the dataset is large because it's not optimized for this one. Just to keep that in mind. But for this dataset, it's perfectly fine. You see, we are doing the spatial join of these two datasets. And you can do the same thing, A route, B route, C route, whatever you like. So you can try to find out, for example. Similarly, you can ask some similar questions. For example, I give you a highway dataset. And I also give you a census block. And I can ask you, for example, what are the, tell me the percentage of different race living within highway I-40 within a kilometer, for example. Right? Can you do that? So we give you a highway data set, right? With all the highways in the US, I give you the Tennessee census block data set with all the populations. So now you have these two data sets, right? You select the I-40 out of the highway data set, and then you do the intersection, or not the intersection, distance within, and then you join these two, and then you can do all the calculation, whatever you like, and then return the result, right? So if you're dealing with two vector data set, yeah, and then you're trying to find the distance or buffer, this is something you can use. And right now we are just returning aggregation, but you can also do different, right? You can, for example, census block, you can say county by county, for example. You can say, for example, the I-40 passing through Knox County or other county, and then you can figure out, for example, which county within certain distance the population might be very different from the general trend, because you might have some certain population concentrated at a certain segment of the highway. Okay, so that's all about the one by one, but you can, so the next example shows you that can do all at once. You can do it for all the routes rather than right now we only do like 8 routes. Right? You can do B, C, D, E, F. Right? You can do it all at once without having to do this one by one. So here, look at this one. So we're going to create a new table for subway lines, and then we're going to create a new column called route, and then char1 basically means just like one character. So what you're doing is create a new table, and you have a new column. That column only accept one character, and then you're going to insert all these values into the data table. So basically A, B, C, D, E, F, G, and you look at this. Right now it's done, but if you want, you can show the data table. For example, here, I think it's what from subway lines, and run it. See? So basically, what we're doing is we are creating a new data table. That data table with only one column, and that column has all these values. This is actually coming from earlier, all the routes from the NYC subway route. Right now we have this one column, and then you can do similarly, you can do analysis with all the population. So basically we're using this one to figure out automatically all at once rather than you have to go through one by one, A, B, C, D, right? So now you can actually get the education. So in this way you can figure out, for example, quickly, okay, which route within which route like the population is different, or which one has the largest black population within a certain route, which one has largest black white population within a certain route. And this is the most complicated one that we have encountered so far. How many lines? Maybe 10 lines, 11. So again, like forget about the select, just go through this first. From the NYC census tract, okay, rename it census, subway, within the distance. So what we're doing here is figure out all the subways, neighborhoods within the subway, 200 meters. And then we join, you also this, yes, like join multiple times. Earlier we joined the subway station, but right now we're joining, say it again. Read what? Yeah. So we're joining 3 data sets. So earlier we joined the subway, and then we joined the line because we want to figure out all the lines all together. But this one is not vector data set. This one is just like number, a string. And then we're showing again on start position subway dot route and line dot route greater than 0. So what this one is doing is that basically we're selecting all the routes pretty much. So in here, and also group by the lines dot route. So the lines is the one that we are doing here, A, B, C, D, all the stuff. And then basically this is the whole code block, okay? And then we are doing return all the population. Again, the line, the route A, B, C, D, and then you see the white population percentage, the black population, and also the total. And then lastly, order by the black population, okay? So basically this one, you can think about executing this code block first, and then this one, lastly, order by this one, okay? So this is like a little bit complicated, but you actually get oops. Something go paste it. Oh, okay. Sorry. Control enter. Again, this one might take a little bit longer because you are doing for all the routes. So you're basically analyzing the entire data set, all the subways, all the lines, and then you're trying to figure out do the sorting based on the result. And this one is not simple inference right now. Like I said, there's no spatial indexing, so it might take but it should be less than 1 minute. And you should see the result. So, but certainly this is a lot more flexible than you use desktop.js. You need to select this one, and then you need to figure out all the routes, all the lines, and then trying to return the result. And also, you can do the rename, right? So if you're using desktop.js, you can only select based on what you already have. You cannot really, you need to rename. If you need to rename the column, it's going to take some time. Okay, it's not bad, right? It's 54 seconds, But now you see, right, from ranking from different routes, A, B, C, D, all the way, and you also see the population in here. So now you can clearly see, if you're sorting by the black population here, for this one is 46%, 46%. So the S route, basically within the 200 meter, within this S route subway line, it has the most black population concentrated within this line. You can go to the end, right? This one is only 30%. So the end route within 200 meters, so basically a lot more white population compared to black population living close to the end subway. And this might be some indication like why. You can look into the map and just see, for example, why certain routes has a certain race or ethnicity population concentrating within a certain neighborhood, and give you all the information. You can sort, for example, how about Asian population, right? And you can figure out which route has most Asian population concentrated within there. So this can give you some like insights about the spatial distribution of this variation of different population and how they're concentrating. You can create some maps. So after doing this, you can show some maps. You can plot all the points, or you can plot the neighborhood, you can plot the streets on the map just to see where they're being located and where which line passing through whatever neighborhood. So that's pretty much it. There are a lot more. Right now we only use two functions, okay? So basically it's just the st intersect and also st d within, right? Here. Geometry doubles basically means the distance. But you can have like disjoint. For example, you can find out which neighborhood do not pass through this subway line, okay? You can also cover or cover by. So it means like if something is totally covered by something, like if you're trying to figure out, for example, which street are totally covered by this neighborhood, like totally within this neighborhood, you can do that as well. Overlap, touches, within, right? So if you need to do something, try to come back to here to look at some of these functions. These are very common spatial analysis or spatial joint function that you can do. Lastly, about some of the projections. So this I think I mentioned before, but I just to make it clear, there are different ways you can do the projection. So DuckDB has this AST transformation that allows you to convert projection. So earlier I mentioned this dataset is using UTM-18, okay, EPSG 26918. But if you want to, you can convert it to something else. So here, if you look at this one, I'm reading this Parquet dataset, okay, and we convert the geometry. Read the geometry. So now you look at this one. This is latitude and longitude. This is XY, longitude, latitude. So XY, point XY. So if you need to, for example, calculate the distance of some data set that's using this like longitude, latitude, make sure that you convert the projection. Otherwise, it's incorrect because they calculate basically the degree. When it's doing the distance calculation, it's like xy minus x2 square plus y1 minus y2 square, and then take the square root. And you don't want to do the calculation based on the latitude longitude because it will be incorrect. When you're doing the calculation, we don't do that on the latitude longitude. We do that on the absolute like distance using meters or feet or whatever, right? So in here, this is the dataset using the cities, and you can use this line to do the transformation to convert the projection to something else. So this might get a little bit like tricky. So select all the star exclude geometry, and then look at this one. Okay, AST transform, and then within there we read this geometry again because it's a Parquet dataset. You need to convert the geometry from binary to a geometry type, and then once you convert this geometry, so what we're doing here is convert it from EPSG 4326 to 5070. So 5070, this one is the corners elbows, so equal area. So this can help you. This one you can calculate the distance and the area, okay. And then the two it basically means you always enforce this one as XY. So if you don't do that, I think sometimes you're gonna error. So basically, when you're passing the data set, it's trying to guess whether which one is X, which one is Y, and sometimes it gets it wrong. So this is actually it's something is I recommend you put in. It's like absolute always XY. So if you run this one, take a look. So compare this one to this one here, right? So this one is XY longitude latitude. This one right now is converted to meters. So for example, all the cities within the US. Now you can actually use this one to calculate the distance because it's projected. The distance makes sense compared to the using the latitude longitude. And then you can save this one as a new table, or you can just do whatever calculation you want to do, certain points, or you can calculate the distance of this one with another data set if you want to. So this is one way you can certainly do that. The other way is you get the data table and then you convert that one to a geodata frame. So what we're doing, you can convert, basically you can project the data within the database, or you can get the data out and then convert the data, the project data outside the database. Okay, so if you need to do the projection within the database, it's this function, st transform. If you want to convert it outside, I can show you here. I think I've covered this one before, right? So what we can do is actually to turn this one to a data frame. So see this one here. I can just do df, okay, equal to, and then df. You might need to convert the text again because it might otherwise not work. You see, now it's looking like this. This is not what we want. So if you want to do the projection outside, make sure that you convert the geometry to text, so that later on we can convert from the data frame to geodata frame. Make sense? So what we can need to do here, it will be what? ST. Remember? S text. And then you wrap this entire column. So now it should come out as this longitude, XY, latitude and longitude and latitude, okay? And with this one, now we can turn this one into a geodata frame, okay? Then it will be GDF equal to leaf map dot df to GDF, okay? And then passing the df. So here, by default, the name is the geometry column. So this is where you can do the conversion. So by default, you know it's EPSG 4326, and then you can specify a DST coordinate system. So if you want to convert to something else, you can do it in here. So you can just pass in SRC, okay, CIS equal to this, and then I can say to DST CIS equal to whatever projection you want to do. But in this case, I'm going to do the same thing, 5070. Okay, and then GDF. It should not take that long. Okay, it's done. So it looks like DuckDB is the more efficient, right? So how long did it take earlier? 0.3 seconds. This one, 9.6 seconds. So it's like how many times difference? So certainly if something you can do using DuckDB, try to do it using DuckDB. It's a lot more efficient than you do it outside. But certainly it's a way you can do it. So now if you compare this one to this one, is it the same? 1194 blah blah. Similar, right? 443. A little bit different, but it should be pretty close. Bumble 11942089. Yeah, pretty much it's the same, right? So now we can do that outside, and with that, then you can start just doing like visualization to whatever way you want. But this is how we can do the converter. But if you don't need it, you can just keep it as it is. Then you'll be just keep it as the latitude longitude, so it doesn't do the what's expected by also equal point. there might be a bug within the function. Let me see here. tst epsg 4326. It's not throw the errors. Otherwise, there might be something. Strings, column. Huh. Interesting. I need to look into it. 3457. What? Oh, sometimes it's just rerunning. I think something is weird. It's not supposed to. Yeah, first time, second. I noticed that some of the DuckDB spatial functions, it worked the first time and you run again. It's yeah, I know that. I don't know. This might something. If you run again, it should work. Anyway, so this is how I can do the converter, and then you can use diff map or longbow to do the visualization. Okay. And that's what I want to cover for this spatial zone. Again, there are more functions you can try it out. But by now, we should have pretty much done with all the basic about DuckDB and then use the vector data. So next week, we may cover some like real-world applications and dealing with large data set, gigabyte, and see how we can use DuckDB to do the data processing. But now you should have all the knowledge you want to use for your final project. So if you have any questions, let me know. And enjoy the break. I will see you next week. Okay.